Yeah, okay. So this is going to be our 18th lecture on power system operation and control. And today we are going to start our new topic, which is optimal power flow. People generally call it as OPF in short form. And OPF is very, very common. As soon as you say OPF to any power system expert, they will easily be able to understand what you're talking about. So just to quickly recap, in the last lecture we discussed quickly about modified coordination equation, and if you have any questions regarding that, you can ask me. And and we also saw how we can calculate these penalty factors using NRLF. We also saw about AGC load flow and how this in practical, obviously there is no case of single slack bus, so there are always multiple slack bus or multiple generators contributing for losses. So therefore we have to use another method, which is actually AGC load flow, where you can get distribute the slack, and the AGC load flow is also called as distributed slack power flow. We we also saw about participation factor and base point concept. So base point is basically where you have a base point economic dispatch solution, and whenever the load is changing based on the participation factor, you can get the economic value of new generation set points without actually running the economic dispatch again. Only a star mark here is that both first and second derivatives of the cost function, or the cost function of the individual generator must be valid. So both first and second derivative should exist. Then only you can run this concept. Otherwise, we cannot do this. So this what we saw. We saw this using this solution procedure, that if this double derivative is not there, then obviously we cannot solve this problem. So that is actually, the double derivative gives us the freedom of participation factor. So this is actually the participation factor. So for individual generator, for total change in load, the contribution of individual generators is actually given by the participation factor. And by this method, you can actually get the new values of the generators at a economical set point. Okay, so we quickly saw one example, and I hope everybody was able to solve it. Anybody tried this example, or are you getting the same answers? This answer, what I mentioned, are you getting these answers? Anyone? Okay, okay. Am I audible, right?
Yes, sir.
Okay, okay.
Yes, sir.
Okay, good, good. Okay, you guys can anyway try. We have given the same problem in the tutorial sheet also, so you can just give it an attempt and try to solve it. Okay, so after that we saw this the limitations of economic dispatch, and what and how we have to actually consider those, and what is the importance of those. So do you remember what was the limitation in economic dispatch in the yesterday's class? I told you about that. Anyone? Anyone about the limitations? There are three limitations specifically. Uh,
Set a line. The limits are
yes, good. One is line flow limit.
voltage and rectifier.
Yes, so voltage and the Q injected by the generators, Q absorbed by the loads, Q generated or absorbed by the line, and the Q by load and generator. So these three are the main factors which are missing in economic dispatch, and uh, as the system was growing and expanding, people started facing issues in these three sections also, or these three parameters are getting violated. So people have to include something in economic dispatch which will make the problem even more accurate or close to reality. Good. So the problem actually started before 1960. So economic dispatch we were doing economic dispatch long back, even before 1950s, and then between 1950 to 1960, this 10-year between, where people started facing issue of losses. So after 1950, people saw the issue of losses, and then after 1960 they immediately started observing the issue of this line flow limit. So what exactly initially people used to do this, you already know that this is the basic economic dispatch format, where we consider that all the generators and loads are connected on a single bus and we try to balance it. But what used to happen is, basically, obviously economic dispatch is giving you economic schedule of generators, but problem happened specifically. This first problem what people observed is that the transmission lines started operating close to their limits. So the issue happened specifically with transmission lines first, and obviously the loads were growing, generators were also new generators were being installed, but the lines were, those old lines were only kept. So people did not expand those lines or did not go for higher capacity lines. So therefore the first issue what they faced is about the transmission lines, and because of which they thought that, okay, in Newton-Raphson or Newton-Raphson load flow, or Gauss-Seidel load flow, when we run, we anyway include the effect of light flows, losses. We also include there, you can also get to know what is the power flow on the line. So all those information you anyway get from a power flow equation, right? In power flow. But the issue was, it was I mean, now when we see it, that it is very simple, but in those days people were unable to visualize how these power flow constraints can be added in a economic dispatch model. So people were unable to visualize it. So in 1962 there was a French scientist, Carpentier. He's a French scientist, and he proposed first time that, okay, we can include, the way we can include power flow constraints in economic dispatch. That was proposed for the first time in 1962, and the way it is done is like this, that the first criteria was that we have to consider all system variables. When I say all system variables, basically voltage magnitude, voltage angle. We have to consider the reactive power of the generators, reactive power of the loads. So with this, the complete variables are considered, and we solve the economic dispatch with power flow constraints simultaneously, or either it's simultaneously or in combination. So we'll see the observations here, and the model which he developed, we'll see that. So this was the first time it was done in 1962. And just for your information, the paper what he wrote, Carpentier, it was not in English. It was written in French, and then probably in 1963 or 64 sometime, some one person from UK or US, I exactly forgot, he converted it into English, and then it got extremely popular and everybody was able to read it and understand it. So basically, when you add power flow constraints with economic dispatch, we call this problem as optimal power flow. Right? So basically, in optimal power flow, just by the name, you can imagine it is optimal power flow. So power flow is anyway considered here. And if the objective function is cost, because in economic dispatch the objective is always cost, that's why it's economic is always for the cost. So whenever the objective function is cost, and where you are solving along with power flow, then you call it as OPF, where we are minimizing the cost. But OPF is very general because it's optimal power flow, so therefore the objectives can be other than cost also. We'll see those things in the coming up slides, but just wanted to give you a quick comparison that when OPF is called, when ED plus power flow is called OPF and when not. So therefore, people, if you just see literature, and also if you, let's say, see some manuals of the system operator and you see the system operation manuals, so you will see that people generally write security constraint economic dispatch. So this is different terminologies what they use. So SCED is nothing but, because we are security constraint, so here security we are providing in terms of power flow, so all the lines are being considered, so that's why we are mentioning it SCED. So this is the basic terminology and difference. We'll again come back to this after completing this OPF model. So if, let's say, if I have to define OPF, so the OPF is basically the determination of the complete state of the power system, so corresponding to optimal operation within technical constraints. So just see here, there are three keywords specifically. One is complete state of a power system, another is optimal operation, and another is technical constraints. So let us see them one by one. Let us see them, what exactly state we are talking about, what optimal operation we are talking about, what are the technical constraints which we have to include in this. Let us see them one by one. So let's say if you have a system like this, where it's a two bus system, so this is actually known as a bus, this is also known as a bus, and if you have a generator connected to it and a load connected to it, so all the generators can generate a real power and a reactive power, PG1 and QG1, or PG2 and QG2. All the loads actually can consume not only just the real power, they also consume reactive power. So it's actually PL1, QL1 and PL2, QL2. And all the transmission lines will have some R plus JX, this is resistance plus impedance. And on all the buses, we have some voltage, magnitude and angle. So V1 is voltage magnitude, delta 1 is the voltage angle. Right. So if, let's say, if I want to know the complete state of a power system, so here what all are the variables? So variables are PG, right? We want to optimally, whatever is the objective, optimally we want to know the real power generator, optimally we want to know about the reactive power generation, optimally we want to know the voltage set points and voltage magnitude and voltage angle, because even voltage has to remain within the limit. So these are the four states of power system. If you know all these four states of a power system, then you know the complete status of the power system. For example, in power flow, let's say in power flow, what are we trying to know in power flow? We want to know in power flow the voltage magnitude and angle, right? So voltage magnitude and angle is not known. We know the PLQL because it's or we assume it's a constant, so we know the load values. We in power flow we also set PG values, right? But we do not know QG values. And why we do not know QG values? Because we do not know V and delta, right? Now only we keep one PG in power flow. We keep one generator as a slack generator so that it can compensate the net. So let me just quickly write it here. So P slack is generally equal to the P load minus PG, all the other generators. This is actually PV bus generators minus or plus P loss. So this is the slack bus, what he has to identify, right? So in a power flow, we wanted to know the voltages and angles. Second, we want to know the reactive power generations. And third, we want to know the slack bus generation power. Right. Now, in power flow, we say that PV, this is fixed, right? We fix PV bus generators. Now, my question to you is, from where we get these values and how we fix it in practical system? We fix this in power system as a PV bus, but from where we get these values? How do we get these values?
From scheduling the load.
Scheduling the load means, can you be more specific?
From the load forecasting, we know what is the load and
load we know from the forecasting. I agree, there is no problem in that. But how we set the PG values for PV buses?
That is from the economical dispatch value. That what should be the value of the PG.
Good.
We have.
Yes, exactly. So we are actually the PG set points are coming from economic dispatch. But in power flow, sorry, your name is Arun, right? Or I'm just guessing from the voice. Huh?
Prasenjit, sir.
Prasenjit, yeah, sorry, yeah. Okay, yeah. So I'm still trying to remember all of your names just by hearing your voice, because I do not see the name who is speaking. Okay, anyways. So Prasenjit, also you can tell me, because for the generators, because generator bus is actually known as a PV bus generator, we also fix voltages. Now, how do you fix voltages a priori in power flow?
That from the reactive power demand. What is the reactive power demand, that according to that?
No, but how will you set the voltage considering the big size of the system? Let's say we are talking about Indian grid. It's a very huge system. There are more than 10,000 generators in Indian grid. So how we will fix the voltage value for all these 10,000 generators? Let's take 10,000 minus 1, because 1 will be a slack bus. Even we actually fix the voltage for the slack bus also. How we do that? Okay, good. Anyways, yeah. Any guesses by anyone else also? How we fix voltage in? Huh?
Transformer.
No. Means I'm talking about that value. So generally we say that slack bus generator is kept at 1.05 or any value. We can set PV buses in power flow, we say in per units, I'm talking in terms of per unit. So let's say we say 1.2 per unit, 1.02 per unit, or 1.01 per unit. We always fix in power flow for all the generators except one, we fix PV bus, all the PV buses, we set the voltage and the PG values. And PG values, as Prasanjit said correctly, that PG values are set from economic dispatch. I completely agree. Now, how this voltages are set?
by power angle, load angle in the generator.
Load angle. No, I'm not talking, because obviously you can control from a generator point of view, you can control these voltages. Obviously, we are going to see that later on when we will study about AGC. We'll see how exactly the generators set these voltages from the mechanical point of view, what all changes they have to do to set they do at their power plant to set that value. That I can understand, but I'm not talking about that. I'm talking how power plant will know that at what value I have to set that voltage.
So maybe for calculating the voltage drop.
But how will you calculate the voltage drop at the first place? Because in voltage drop you will only know once you run a power flow,
Yes.
right? Then only you will get the voltage drop, right?
Design value of transmission and
Sorry, once again.
yeah, from the design view.
No, we can actually change. We can, generator can, as one of you has already said. I think Adam or I don't know who said. So one of you said that the voltage can be changed by the excitation or the in the power plant. There are a lot of mechanism how you can control the voltage and set the voltage set points. I agree on all those points. My question is how a power plant will decide that at what value I have to set.
Zero excitation system.
Huh?
Zero excitation system. Excitation system.
No, I agree. Excitation systems are used to set that voltage, right? I agree. But you can, as a power plant owner, if I let's say give you, you are a power plant owner, obviously you can set the excitation system such that the voltage is either 0.9 per unit or 0.95 per unit or 1 per unit or 1.05 per unit or 1.01 per unit or 1.1 per unit. Any value you can set. Right. Now my question is, how will you decide at which value you can set? You have to set. Which value you have to set? How will you decide this?
It depends on the type of the transmission. Is it for transmission or for distribution?
No, transmission. We are talking about transmission. We are talking simply in power flows for the PV bus generators.
Losses.
No, again, losses is you can get the value of losses after running power flow, right? Because for getting losses, for getting all the voltages values for on the load buses as well, that you get the values after running power flow. But to run a power flow, you need to set voltage values on the PV buses before. That is an input. It's an input value, right? Is it Newton-Raphson power flow? Is it covered in your CAPSA course, computer aided power system course? Is it not? I'm not sure. Or you have studied power flow, right, before in your bachelor course?
Yes.
So in power flow, that is the basic fundamental. There are three types of buses. One is slack bus where you set V theta. There is one PV bus where you set P and V, and there is a PQ bus where you set P and Q. Now my question is, how will you set these values? Then only if you set these values, then you will run the power flow, then you get all the values of voltages and angles, and then you can calculate the losses, everything you can calculate after that. But my question is, how will you set these voltages a priori before running the power flow?
I can't. Just I will make initial value and start to solve it, and then make an iterate vision to solve another value.
Okay. Yeah, it's kind of a good answer, but yeah, that we cannot do in practical. There are few regulations that your voltage has to be maintained within a particular bound. So yeah, okay. Let me tell you this. In this optimal power flow, basically that voltage values, similar to economic dispatch, what Prasanjit said, that we get the PG values, this PG values we get from economic dispatch. I agree, completely agree. I agree that you get from that. But the problem is, we also need the value of voltages, right? In power flow, that value of voltage in olden days, before 1960, or even today also, I would say, at in some of the countries, these voltages are set at a random set point with some logical, there is some logic behind, but there's no hard and fast rule to set at that value. It is just a random logic which people use. But in most of the places, there has to be something which will give the correct value of voltage to these generators to set their generator at this voltage, or to set their generator to generate this voltage set point. So in OPF, optimal power flow, you will see that these voltages, all these voltages and these PGs, these are variable, and these value of voltages you actually get from OPF. So OPF is the key for all the means all these questions. So all these set points, initial inputs, what we give, it is all coming from OPF. You will see that gradually. Good. But anyways, I knew that you did not know this. That's why you were just going around here and there. But it's okay. It's okay. But you got the idea that all the set points in power flow, we do this for using or running an OPF problem, right? Because in economic dispatch we do not consider voltage, we do not consider reactive power. So that's why it was of very elementary use. I'll tell you at the end where economic dispatch is used and where OPF is used, but you got the idea, the difference between economic dispatch and OPF. So let me just go ahead. You will get you'll be able to appreciate the beauty of this algorithm and this method. So in this complete state of power system, we will actually run all the in OPF, all these are variables: PG, QG, V and delta. These are variables, and these are the input values. We assume that it is constant, or we assume, as one of you has already said, from the forecast we get the values of load PL and QL. And line parameters we already know from the design or manufacturer rating. We know all the R plus JX, these values is already known from the manufacturing rating. Right, now let us go ahead. The next keyword here. So the next keyword is technical constraints. So here the technical constraints what we have to put in OPF is basically the limits on generators, because we want the generators to operate at their within their limits. Now from the generators, I also told initially, do you know from where we get the generators limit? I told this before. How do generators decide what is their maximum PG limits? PG and
from the turbine and boiler consideration.
No, that is the max and min limit, but that is okay. What you said, it is fine for economic dispatch, I agree, but it is fine because there we were not considering about QG, reactive power was not considered. So there is one more thing on top of that which actually decide the limits of PG and QG. I already told you that before. Huh?
Power factor of the generator.
But how do you decide this power factor of the generator? Because you can control PG of the generator as well by running the turbine. You can also control the QG of the generator by changing the excitation system. So power factor you can always change of the generator. But how will you decide that power factor? I can give you a hint. It is from the design, but based on what? Means what is there in that design? So let's say you are the manufacturer of a generator. What detail you will give to the operator or the power plant owner, or there should be some manual, right? How do you see that? There's some chart graph is there.
Harmonic
There is one.
speed of the rotor.
Yeah, you can vary that speed. Obviously, there is going to be the maximum speed, minimum speed. Yeah, that is all there. But there is one graph.
Thermal limit or
No, no,
current
no.
limit that
No, 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 no. Did I mention about this? I think I mentioned about capability chart. Are you guys aware of this capability chart? I mentioned this. I remember I mentioned this during the initial lectures. Do you know what is the capability chart of a generator? What is there on x-axis and y-axis? Any idea?
Sir, PG and QG.
Yeah,
They're
exactly.
basically
So
for governor control and excitation control.
exactly. So P and Q is there. So whenever there is means when you, let's say if you are a power plant owner and you go to a generator company, manufacturer company, and you want to purchase a generator. So like when we go to buy anything, let's say if we go to buy a laptop, we say a lot of configurations are there, different configurations are there. So similar to that, when you go and buy a generator, first thing what you look at is this capability chart. That is the technical comparison, and then obviously based on your budget and all, you decide what type of laptop you want to buy, and similarly what type of generator a power plant owner wants to buy. So first thing you always see capability chart. So you can just do a quick Google search and find out capability chart, the details here. I'll give you a quick brief introduction here. So capability chart is basically there is one curve is there. This line is corresponding to the this what we call it, this is stator current of that generator, and then you get this curve. This is for the armature current, and then based on the rotor speed, there is some limitation of rotor speed, so based on this you will get, and the field excitation also is there, so based on this you will get this limit. So eventually, let me quickly change the color, it will give you, so eventually this curve, it is not jerky, it's actually a very smooth curve. So this curve is actually known as, what I have drawn in blue, this is the capability chart or capability curve of a generator. What do we mean by this curve is basically, in x-axis, just quickly for a reminder, x-axis it is P, y-axis it is Q. Now let's say you want to generate a value 0, right? When you want to generate 0, P will be 0, but Q max and Q min will be this value. So this will be Q max and Q min. Now if you want to generate a P value here, then this will be the maximum Q which you can generate. This much is the maximum Q which you can observe. So a positive is generate and negative is absorb. So in one way it is acting like capacitor, in one way otherwise it is acting as inductor. Now if you want to generate at this value here, maximum value, so here your PG will be that value, but QG will be basically 0. You cannot provide reactive power. So also in power flow, you also get one more information in power flow. For PV buses, you also get to know what is the reactive power generation limit of those generators. So I should have actually asked that question, but the reactive power generation limit of the generators actually come from this capability curve. And the max, what I think Nivedita said, the max comes from the turbine limits, this maximum value, and the minimum this is, I'm keeping it 0, but it can be, let's say 0 is here and it is starting from this value, so it will be a Pmin value which will come from the boiler limitations. So that is there, that logic is anyway there, so I'm not disturbing that logic, but only thing is that the Q limits of a generator or reactive power generation limits of a generator comes from capability chart or capability curve of that generator. So generally when you go to go to let's say a generator company to purchase a generator, they will always give you this capability curve, and obviously based on the type of generator, like let's say it's a coal based generator or diesel generator or a gas generator or a nuclear generator, every generator has its own typical capability curves and type of means there is a specific type of generator what you can use based on the type of raw material, so the way you want to generate power. So this is the capability curve from where you get the value, or if you just draw it very smoothly, it generally looks like a curve like this. So if you are here, you can generate less amount of qg and your qg max and qmin will be a small value. If you are let's say here, so you will have a higher value of q max and qmin to generate and absorb, right? So this is the technical constraints. So basically when we this is not there in economic dispatch. Now you can see economic dispatch, we were only considering about these horizontal limits, but we were not considering about the q limits. But now when we are including the effect of voltages, we have to include the effect of q also for the generators, and when we have to include q, that q limits comes from the capability curve of the generator. So now I hope it is clear to all of you how this q limits come. Now the next issue was there with the transformers and transmission lines, because all these transmission lines and transformers have some power carrying capacity. So let's say if I write apparent power Sij, so S is basically apparent power, Ij is the bus between which it is connected. So let's say it is connected between bus 1 and 2, so it will be S12. So obviously S12 will be having I'm drawing this upper line for the upper limit or the maximum limit, and obviously the power can flow in the reverse direction at the same value, right? So let's say if a line is there, so let's say if I just talk in terms of number, so if it can carry 100 MVA, so it can carry same minus 100 MVA in reverse, right? It's clear, right? So it will be the same maximum value. So current, whatever current is going in forward direction, the same current can also be taken care in the reverse direction in lines and transformers. So it will be this limit is going to be there on the apparent power flow of a line and a transformer. So this is also we were ignoring in economic dispatch, and this we are going to include in OPF. Now one thing which is remaining is bus voltages. Right, now from the rating of generators, as well as if you see your appliances at your home, either you take your laptop charger, mobile charger, refrigerator, air conditioner, tube light, fans, any appliance you take, you just see the rating and you will see that you will always find a voltage range between which it will operate. Right, so that voltage range is generally 0.9 to 1.1. So it's per units. I'm talking about per unit. So it is nothing but plus minus 10% of the nominal value. So nominal is generally in India it is 230 volts. So it is generally plus minus 10% of 230 volt. Again, I'm talking in terms of per units. I'm not going into that. Everyone knows that what is the importance of per unit. So even if you are at higher voltage levels, let's say 11 kV, 33 kV, 66 kV, 110 kV, 220 kV, 400 kV, 765 kV, everywhere this voltage or per unit concept is going to be same. So it is always going to be plus minus 10% everywhere. So we want to ensure that the voltage is always between plus minus 10%. And generally for the generators, this is for the loads. So this is for the loads, basically load buses. And generally for the generator but buses, we keep just 5%. Oh, sorry, I wrote it in reverse. So this is for the generators because generators have more margin to fluctuate, and this is for the loads. Loads generally we keep plus minus 5%. So this is generally 5%. But again, this plus minus 5% or plus minus 10%, this is the logic of the regulator. So I hope you remember from the starting lectures, we discussed about the importance of regulator. So these regulators decide the voltage percentage margin what every system operator has to ensure, and all the generators have to ensure. So this value is decided from there, but generally it is plus minus 10% in most of the countries, and for loads it is plus minus 5%. So for general sense we will keep plus minus 10% for in our theory class, but obviously in practical things can be different. Now, I hope you got the idea of technical constraints. Now, let us see the third quantity which is missing is optimal operation. Now, in optimal operation, can you guess what could be the optimal operation? One is obviously you know that cost minimization or the economic dispatch is one of the objectives. What else? What are other objectives can you think of? What we want to use in power system? If you want to run power system, what all objectives you can think of? In economic dispatch, the objective function was cost, but other than cost, what all objectives can be there? Can you think of any other objectives?
Stability of the system. Stability.
Stability is a dynamic concept. Maybe from the steady state I can think of voltage stability. People do consider voltage stability. That is one of the objective. Good, that can be there. Any other objective what you can think of? Any other objectives? There are many objectives.
Load demand.
What do you want to do with load demand? Minimize the load demand, maximize the load demand, what?
To be constant, not.
Because objective is always either you have to minimize or maximize. Again, let me ask about this voltage stability. We want to minimize the stability or maximize the stability?
Maximize stability.
Yes, it's going to be maximize. Load, you were talking about load. What do you want to do? Minimize or maximize?
I want to maximize load also.
Yes, load will also be maximized because we want to compensate for all the loads possible. Maximum load we can satisfy, because at the end power system generator will only generate if loads are there. If loads are not there, then what is the use of generator? So that's why we want to maximize the loads. Any other guesses?
Losses can be minimized.
Good, very good. Minimize the losses. Is it the real power loss or the reactive power loss or the apparent loss? What? Or anyone?
So, any loss.
Yeah, it can be anyone. It can be anyone. Yes. Any more guesses?
Emission can also be minimized.
Good. Yes. These days, people are talking about the pollution. So yes, emission is also one of the factors. Because especially the coal-based power plants, diesel-based power plants, gas-based power plants, these three power plants generate a huge amount of emission, and they generate a lot of sulfur and carbon and nitrogen oxides in the air. I mean, the exhaust generates the lot of values of gases which are not good for human being. So yeah, good. So yeah, obviously you can think of many more objectives these days. Lot of new objectives which are coming up. People are trying of lot of different objectives, but obviously the cost is the major objective what is often used in OPF, and we always want to minimize the cost. That is one of the major objectives. So again, just to come back, when you include the technical constraints what I have shown you just now, if you include all the complete state of the power system which I have just shown you with the cost objective, which is economic dispatch, and those constraints were with power flow, then you call this problem as SCED. And this problem is actually terminology is often used in the real practical systems. So whenever they are talking about SCED, that means they are running an OPF where objective function is economic dispatch and all the power flow constraints are there. And there can be other objectives. Yes, one is minimizing total system losses. Generally, minimization of system losses, we wanted to minimize it for the distribution system. So if you are running a OPF in a distribution system, we minimize the losses. Generally, this is not there in transmission system, because in transmission systems the line resistances are very low or very less values, so therefore the I square R losses are very less in transmission system. So generally this is an issue of the distribution system, because in distribution system R by X ratio are high compared to the transmission system. So that's why we want to minimize the resistance, resistances are higher, so therefore we want to minimize the current, so therefore the reactive power I square R losses is less. So losses are generally the logic of the distribution system, not for the, but yeah, people do run for transmission system as well at times, depending on the system size. So let's say if you want to talk about, let's say if you talk about Sri Lanka, I'm just giving an example, Sri Lanka or Lakshadweep and Andaman and Nicobar are two small islands of Indian grid. Obviously they are not connected by the main grid and they are islanded. There's a small grid, small systems, power systems of their own. So there you also have to consider for loss minimization, because they are of a small size, and considering the size of India, obviously you do not need to consider the loss minimization in the transmission system. Okay, good. Now with all these constraints, let us see the mathematics and how exactly problem looks like. So the OPF problem is actually looks like this, where you have an objective function. This could be anything, either cost, loss, emission, voltage stability, load maximization, any objective can be there. I'm just generalizing it by minimization. If it is the objective function is required to be maximized, you just add a minus sign. This we saw previously in canonical forms and linear programs. So just add minus sign. So I'm writing it a very generic sense. You can have some set of equality equations, some set of inequality equations, and their dual variables. Right. So in power system, the equality constraints are always power flow equations or power balance equation. So we saw in economic dispatch, the power equations was sum of PG should be equal to PD. This was the only equation. But as soon as we are including the effect of power flows, here the equality equation will be like this, because we have a system like assuming for a bus, then you have to write for all bus that PGI minus PLI, so whatever is the generator value minus the load, should be equal to this VI Vj Yik cos theta ij minus delta I minus delta k. So this equation you have to write, and now you can see here we have included all PG, QG, V and delta, and all four parameters are here, and this is the equality equation for the real power. Similarly, because we are including the effect of reactive power, so all the equations for QG minus QL is equal to VI Vj Yik sine delta I minus delta k minus theta ik. You can also write it like theta ik minus delta I plus delta k. We can just, and then you can add a minus sign here. So either you do that or do this, both is going to be the same. I just represented it in this fashion. So this is one power flow equations which is going to be there. Now if we talk about the inequality constraints, so let's say if you talk about inequality constraints, there will be inequality constraints corresponding to the real power generator, its maximum limit, minimum limit. There is going to be the reactive power generation limit, which is going to be maximum QG max and QG min. You are going to see the voltage max and voltage min limits, and you are going to see the line limits. And you think keep this observation that Sij max is there, only I'm adding a minus sign because obviously in both the directions the power flow is going to be the same, means maximum it can take. So line will have can carry the current of same capacity in both the directions, right? So this is the OPF inequality constraint. So I hope you got the idea about the equality constraint and the inequality constraints. And lastly, let's assume the objective function is cost. Let's assume that. So there will be a cost function, which is where we saw similar to our economic dispatch. So this is going to be your cost function. Now the above model, what you saw this cost function. So here it is cost function. Here it is power flow equations, both for Q and P. Here you saw all the limits on PG, QG, V and Sij. You saw all the limits. Now this problem is specifically known as AC OPF. Why AC? Because we are considering all the AC components, because reactive power is only there in AC. The voltage angles appear only in AC. Obviously they are not there in DC. So this model is actually known as AC OPF, alternating current OPF. Now can you think of one quick question? This model is convex or non-convex? And with this I'll end this today's class. Is this model convex or non-convex?
It is convex, sir.
Why?
Because all the values will be in the limit.
No, means convex when say basically because I'm not going to, because there are terms like if you see the equality equations, it is not convex actually. If you see the equality equation, so this is the equality equation. You can see here that this voltage is a variable, this voltage is a variable. You have this delta I and delta J also as a variable, and this is in the trigonometric sense. So you can see here, if you have to plot this equation on the right hand side, this is going to be somewhere here in a sine wave or a cosine wave will be there. So it is going to be extremely non-linear, or it will be an extremely non-convex equation. So I would like to end this with this note that this problem of ACOPF is extremely non-convex, extremely, I'm emphasizing that it is non-convex, and it is actually extremely non-convex because you have the multiplication of two variables. This makes it non-convex. You have a cosine variables inside a cosine term. This also makes the problem even more complex, right? So this problem is heavily non-convex, and as soon as it is non-convex, I told you before that the solution could be local. It will so solution could either be here or here or here, wherever it is, based on the starting guess. From the Newton's method, wherever we give the starting guess, it will run based on that. So if let's say if the starting guess is here, it will follow the gradient, and wherever all the KKT conditions or the slope becomes 0, it will stop there. So you can see here that there are going to be multiple solutions for it, and this problem becomes really difficult to solve in practical situations. So with this, I'll end this lecture, and I'll tell you in the next lecture how to simplify this problem for practical usage. Let us see that in the next lecture on Monday. Is it fine? Do you agree that it is non-convex?
Yes, sir. It's not convex.
Yeah, it's extreme.